This is the notes for section 9.4. Feel free to hit pause. That way you can just copy down what you need to copy down at your own pace. But other than that, I'm going to try to go through it real quick because, like I said, you can pause this. All right, what we were talking about here is inscribed angles and polynomials. Basically, angles and quadrilaterals, essentially, drawn into a circle. So, first definition, inscribed angle, basically, vertex on the circle. So looking over here at point A, we have angle BAC. That is an inscribed angle because the vertex is on the circle. Now, more importantly, the intercepted arc. It is the part of the circle that is on the interior of the angle. So if I were to extend out those sides that form the angle, the part of the circle that is on the interior of the angle is this arc that I'm drawing here in blue. That is the intercepted arc for that inscribed angle. Okay, there's going to be a relationship between those two things. We'll get to that in a second. The other thing, looking at the bottom part, an inscribed polygon, basically it is a polygon, whether it's a triangle, quadrilateral, we're going to be talking mostly about quadrilaterals, but all of the points are on the circle. Again, there is a property that goes with that. Sorry, the window was a little bit too small, so a lot of notes didn't show up, but that's the idea. Those are the things that we're talking about. So, the first property, this is the big one we're going to use the most. An inscribed angle. Angle ADB is an inscribed angle because that vertex point D is on the circle. The intercepted arc is AB. The measurement of that angle is half of that intercepted arc. Okay, that's our relationship. So here's just a little drawing that's just to give you a visualization of it. We got arc CB, that is this red one, that's 100 degrees. This angle A, where the 100 degree marker is right in here, that is the central angle. So like we talked about before, central angle and arc are always equal to each other. But angle D down here, this 50 degrees that I'm moving around, that is an inscribed angle because the vertex D is on the circle. This angle is always half the intercepted arc. So it doesn't really matter where I draw the inscribed angle. Vertex is on the circle, it's always staying 50 degrees. But if I change the intercepted arc, you can see how the arc is twice the measure of the inscribed angle. The other way around, the inscribed angle is half the intercepted arc. Okay. If you have two inscribed angles on a circle that intercept the same arc, those angles have to be equal. So the two inscribed angles, angle ADB, this angle, it is intercepting arc AB. Then we have the other other inscribed angle, angle ACB. It's intercepting the same arc. So if this arc was 50 degrees, this angle here would be 25 degrees, and so would that. So if two inscribed angles intercept the same arc, the angles have to be equal. So angle ACB, just fill in that line. Okay. Two inscribed angles intercept the same arc, the angles have to be equal to each other. Same idea here. Here's just a big drawing. With a couple of inscribed angles intercepting the same arc, that's this 50 degrees here. It doesn't matter where we move those vertices, as long as the angle stays an inscribed angle. These three angles are always intercepting the same arc. Those three angles are going to be equal. All right, so in example 1, find the indicated measure in circle P, measure of angle S. This is angle S right here. Because the vertex is on the circle, it is an inscribed angle. Its intercepted arc is arc RT, which is 60 degrees. So the inscribed angle is half the intercepted arc. Okay, so angle S, 30 degrees. For arc QS, here's that arc. The Inscribed angle, that is intercepting that arc, is angle R. It's 37 degrees. So if we take the inscribed angle and double it, 60, 74 degrees, we've got our intercepted arc. Okay. In example 2, find the measure of arc HJ and angle HGJ. What do you notice about those two angles? All right, so arc HJ, that's this one. Here is its inscribed angle intersecting arc HJ. So if we double the 39 degrees, we get 78. There is arc HJ. 78 degrees. All right, this is the idea of what we're looking for with this section. We're also finding the measure of angle HGJ. Okay, angle HGJ is this. It is an inscribed angle, but it's intersecting the same arc. So those angles are going to be equal, 39 degrees. What do you notice about these two angles? Well, they're congruent, because they're both inscribed angles and they're both intersecting the same arc. Name two pairs of congruent angles in the figure. All right, so I'm going to look at arc RS to start. That arc is being intercepted by angle P, and it's being intercepted by angle Q. These two angles are intersecting the same arc, so they got to be congruent. And we can do the same thing with the other two, angle S and angle R. There's angle S, it intercepts arc PQ. Angle R intercepts the same arc. So angle S is congruent to angle R. All right, in example 4, find the value of x. So this 5x at angle A, first off, angle A is on the vertex is on the circle, so it's an inscribed angle. So the angle is equal to half the intercepted arc. The intercepted arc is all of this, arc BC. That's the 9x plus 21. Okay, that's our setup with this. The inscribed angle is half the intercepted arc. Now, to solve for x, we could distribute the 1/2, but I'm going to go the other direction. I'm going to multiply both sides by 2. That gets me 10x here. Half times 2, they cancel each other out. That leaves us with 9x plus 21. Subtract your 9x from both sides, you get 1x equals 21. All right, that's how we do those kinds of problems. Two more properties. Again, go ahead, hit pause, copy these things down, take a look at them. These are just kind of corollaries to these properties. I'm not going to do the proof of them, but if you just kind of think about it a little bit, the logic should make sense. The first one here, Inscribed Right Triangle Theorem. If a right triangle is inscribed in a circle, so inscribed in the circle means that the 3 vertices are on the circle. There's our right angle. Angle B, because it's on the circle, it's an inscribed angle. The intercepted arc is this semicircle. That's 180 degrees, so the intercepted arc is 180, the angle is half. That's why the hypotenuse is going to be the diameter of the circle. On the right side of the screen, quadrilateral is inscribed if and only if opposite angles are supplementary. So when you have a quadrilateral where all 4 vertices are on the circle, the opposite angles are supplementary, meaning this first one, angle D plus angle F, you add those up, you get 180. Angle E plus angle G, you add those up, you get 180. But that only works when all 4 vertices are on the circle. All right, real quick, in example 5. Find the value of each variable. Okay, all 4 vertices are on the circle, so opposite angles. 100 plus y, those are supplementary, so they have to be 180. Subtract your number from both sides, y is 80. Same thing with x. Opposite angles, 88 plus x, Those are supplementary, so they add up to be 180. Subtract your 88, you get 92. In example 2, a right triangle is inscribed in a circle. It's always helpful to have a picture. There's your right triangle. All three vertices are on the circle. The radius of the circle is 5.6. Again, if it's a right triangle inscribed, the hypotenuse is the diameter. Kind of a junky drawing, but that means the center of the circle is at the midpoint of that hypotenuse. So the question is, what's the length of the hypotenuse? Well, if 5.6 is the radius, this way, it's got to be 5.6 on this side. So the length of the hypotenuse, 5.6 plus 5.6, we get 10, 11.2. All right, that is it. Take care.